In this video, we'll start the study of the properties of convergent series. We'll learn techniques throughout the next few videos which can help us decide whether an infinite series converges or not. The first thing we'll learn is the vanishing test. This will be a necessary condition for an infinite series to converge. The proposition is called the vanishing test, which says that if the infinite series the sum of ak with k going from 1 to n converges, to a sum S, then the general term in the sequence, in the series, these numbers, the sequence that we started from, it has to converge to 0 as k goes to infinity. So the terms in the sequence individually have to converge to 0 if our series is convergent. Okay, so this is the vanishing test. Let's prove this quickly. By our assumption, by definition, our assumption that the infinite series converges, remember, means by definition the limit of partial sums has to converge to this sum S. And also it's the same limit if we we shift the index of our partial sums by 1. Okay, so let me just say that this is also a convergent sequence, this partial sums with n-1 terms, and it should also converge to the same sum S. Okay, since an, the nth term of our infinite series, is equal to the nth partial sum minus the n minus first partial sum, because here we are adding up the terms from a1 to an, here we are adding up terms from a1 to an minus 1. So if we take this difference, the an term remains. So we get, when we take the limit of an, with n going to infinity, it's the same thing as taking the limit of this difference of partial sums. But of course, we can take this difference, we can take this limit by taking the limit of each of these terms and then take the difference. This is what we have learned when we have looked at the arithmetics of limits. So just like the sum of limits, we have the limit of sums. For the difference of limits, we have the limit of the difference. So this is just simply s minus s, which is equal to 0. And this concludes the proof. So we have seen that the general term in the sequence must converge to 0. Okay. Now at this point I should make it clear that the vanishing test is a necessary but not sufficient condition of convergence. So by this I mean, if you have an infinite series for which the general term converges to 0, it doesn't imply that the series is going to is going to converge to some sum. Okay, it's the other direction. If we have convergence, then the general term has to go to 0. So a good example, see the harmonic series from the last video, the sum of 1 over k, with k going from 1 to infinity. So the general terms in this series, 1 over k tends to 0, goes to 0 as k goes to infinity, but this infinite series is divergent. We have proved that in the previous video. The way we can use the vanishing test is the following. If the general term in the series doesn't converge to 0, then our infinite series must be divergent. So it's the opposite, it's divergence that can be established using the vanishing test. So if ak does not go to 0 as k goes to infinity, then the sum, the infinite series, is divergent. Okay? Now and the way we express this is by saying that if a series fails the vanishing test, then it's divergent. So let me give you 2 examples for this, just to test your understanding. The first example I want you to consider is the infinite series that you get by summing, by adding up the numbers k divided by k plus 1, with k going from 0 to infinity. Well, we can take it from 1 to infinity. Okay, what do you think about this sequence? Pause the video, think about the vanishing test, apply the vanishing test to this infinite series, and decide whether it's a convergent or a divergent series. Okay, I hope you paused the video and found that in fact ak is now k divided by k plus 1, and this converges to the number 1 that is not 0. That means, so the series fails the vanishing test meaning that it is divergent. The sequence of partial sums won't converge to any number, it will be divergent. Now for the next example, I want you to consider the sum of squares of the reciprocals of square numbers going from 1 to infinity. Okay, so what about this infinite series? Apply the vanishing test and input your answer, and you choose the option that is correct below. Okay, I hope you paused it and have found that now what we have is ak being equal to 1 over k squared, which does converge to 0 as k tends to infinity, meaning that this infinite series passes the vanishing test. It does satisfy this condition, but that does not mean that the series has to converge. So it's very important that it passes the vanishing test. So it can be convergent. That is all we can say when a series passes the vanishing test, that it can converge, but we are not sure. This is not conclusive evidence. Okay, I hope you enjoyed this video, and I'll see you in the next one.